So get the recording going to the cloud. So we have, again, page 26. We're looking at the general addition rule. And this is where we left off last class, where it's like, you're going to add probabilities, but then at some point you're going to subtract off if necessary. Hold on one sec. My son. All right, sorry about that. There was an emergency music project situation. So anyway, we have the sample space here of the deck of cards. And what we want to do is answer the questions that are related to them. But we got to be careful about determining which instances are mutually exclusive, also known as disjoint, or not mutually exclusive or disjoint, right? So the mutually exclusive event, and again, it's the same thing. These two terms really mean the same thing in this context. This is the instance where you have two sets that do not overlap. So set A, set B, no overlap. All right, no part of set A is also set B, and no part of set B is also set A. All right, got some folks coming in. All right, so if it's not that, then we have to subtract off a probability value. All right, so this only happens if there is overlap. All right, so that would be the case where you have one set that intersects another set in some way. All right, I was going for perfect circles, but I'll take what I can get. So you have A, B, and then you have that overlap that represents the set of A and B. A little obnoxious on the highlighting there, but that's what I'm going for. All right, so those are the things that we have to take into account, because if there is no overlap between the two possible outcomes, then you just add the two probabilities and that's the end of it. All right, so we got to be mindful of that, but it's really not in the cases that I'm going to give you a case of mental gymnastics, because you should be able to determine very quickly whether the two sets overlap. All right, so in the case of part A, we have the probability of getting a 7 or a king. All right, so if you're following this rule to the letter here, you might say, all right, this is the probability of getting a 7 plus the probability of getting a king minus the probability of getting a card that is both a 7 and a king. All right, now when you look at it in that context, you might say, oh, well, looking at the cards, here's my kings. I'll use a better highlighter there. This is my set of kings. And this is my set of 7s. There's no way that you could have a card that is a 7 and a king at the same time. All right, so that makes this unnecessary, irrelevant. All right, and that's because there is no overlap. These are mutually exclusive events. All right, so all we'd have to worry about here is taking the probability of getting a 7 and adding to it the probability of getting a king. All right, the probability of getting a 7 is 4 out of 52. There's 52 cards in a deck, 4 of them are 7s. Right, it's really as simple as that. For the king, same deal. There's 4 cards in the deck that are kings. There are 52 cards in a deck overall. So the probability is going to be 8 out of 52. Now, if you have the sample space written out or drawn out, it might just be a matter of going through and counting the different outcomes that you're looking for. All right, I'm looking for the 7s and the kings. So I'd look through and I'd say, okay, well, where are my 7s? There's 4 of those. Where are my kings? There's 4 of those. It's a total of 8 cards. Like I'll win if I get any of those cards. All right, so that's really all there is to it. Now, in the case of part B, 7 or prime, different story, right? Because you have cards that are both 7 and prime at the same time. And that's only because 7 is a prime number. All right, so let me get the list of primes here, the relevant ones. You have 2, 3, 5, 7, and then after that you'd have 11, but there is no 11 in the deck. 13, 17, and so on, right? 23, not relevant because out of the deck of cards here, I max out at a 10, right? So I would only want the cards that are relevant, or the numbers that are relevant to the deck of cards, all right? So when I look at this one, I would say the probability of getting a 7 plus the probability of getting a prime number minus the probability that the card is 7 and prime. All right. So since 7 is a prime number, all we would have to do is figure out the list of primes in the deck because it will already have included the 7s. All right. That's a more intuitive way of going about it. But if you wanted to go by the formula, so by the book, you'd look at the number of ways you can get a 7. That'd be 4 out of 52. Then you'd look at the number of ways in which you can get a prime. So a 2. Oh, let me go green here. 2s, 3s, 5, and also the 7s. All right. So I can get rid of this highlighting for the kings. All right. So in the deck, there's 16 cards that are prime out of 52. But because you have a set of cards that are both prime and 7, this would be my overlap, I would have to subtract that off. Right? The 4 cards that are both 7 and prime. And so if you look at it carefully, you'll see that we have a 4 out of 52 here and a negative 4 out of 52. Those two numbers are exact opposites of one another, so they would cancel, which means that 16 over 52 was the only relevant probability in this. All right, so these would go away because they're exact opposites, and we know that exact opposites cancel to equal 0 when you add them. All right, so the only thing that's left is the 16 out of 52. Now, if you carried out the addition, 4 plus 16 is 20, minus 4 again is back to 16. It would cost you an extra 5 seconds of work, but in the end, it's going to give you the same thing. All right. Then we have prime or even. If I look at my set of primes here, I see that one of those numbers is even. All right. So I'd have to account for that by saying that there is overlap. All right. So probability of getting a prime number plus the probability of getting an even number minus the probability of getting a card that is prime and even. I guess I can reduce the spacing here a little bit, and then I'll shrink it down just to make it fit. All right. So the primes, we discussed that in the last problem. There's 16 out of 52 cards that are prime. Now for the evens, so we go back to the deck of cards. Yeah, kind of like sort of take it from scratch here. Let me see if I can extricate here. Yep. So these are my prime numbers. Honestly, I don't want to zoom in just yet, but I really can't see. I think it's right there. All right, so those are my primes. Then I would want to look at my even numbers. All right, so let me get a purple involved or whatever that color is. So here's an even one. Here's even, and even. All right, so I have 1, 2, 3, 4, 5 instances in which a card is even times 4 because there's 4 of each instance. All right, so we have 4 cards that are all the same number. So I have a total of 20 even numbers. All right, we already know the 16 primes, but now I have 20 evens. Now I want to subtract over any instance where there's overlap, and that only happens in the one case. The case of the number 2. Oh, the arrow didn't come along with it. Ah, come on. Crying out loud. You know what? I'm just going to make a new arrowhead. All right, so that would be this instance right here, the case of the number 2. And I'll just toss this one. All right, so there's only one number that is both prime and even, but that one number occurs 4 times. So I have to subtract off 4 out of 52. All right, so 36 minus 4 is 32 out of 52. So we have 32 instances where you could have a card that is both, or I'm sorry, either even or prime. And the last one, probability of 7 or not red. You'll notice that at this point, the calculator is really just for show because the numbers are pretty easy to work with. But we'll get to the cases that involve a calculator in a little bit. 7 or not red, that's a little trickier. The not part kind of throws you for a loop, maybe. But when you think about something that's not red in terms of a deck of cards, if it's not red, then it must be black. So this is really saying find the probability that a card is 7 or black. All right. The probability of 7 or black and 7 or red would actually be the same thing because there's an equal number of red cards and black cards in the deck. But if we're just going through the process, probability of 7 plus the probability of black minus the probability of 7 and black. All right. So we know that there's 4 cards in the deck that are 7s. Half of the deck, half of the 52 cards, half of the deck of 52 cards. So half of the deck of 52 cards would be black. So that's 26 cards in total. But then we'd have to subtract off any instance of overlap, a card that is both 7 and black. So that would be the 7 of, forgive me, that's how I make a club. 7 of clubs, 7 of spades. All right, so that's a total of 2 cards in the deck out of the 52 available. And so 4 plus 26, 30 minus 2, 28. So 28 out of 52 would be the probability. All right. So when you have the sample space in front of you, it becomes a lot more manageable. There are instances where you might consider drawing out a sample space, but every time I give a test on this unit, I always, whenever I ask for addition or multiplication rule, which we'll get to in a minute, whenever I ask those kind of questions, I always throw in a sample space for you, and it's just easier. It's not necessarily going to be an ordinary deck of cards, but I'll give you an image that is a sample space and ask you a variety of probability questions related to it. You'll see when you get into the practice test. But we're not finished with the unit, so there's no urgency just yet for that. But like I said, for 27, 28, I wanted to grab a problem or two and just kind of take you through it, because when you're dealing with, well, cards specifically, but any kind of probability instance, you could have what we call independent events, or we could have dependent events. Independent events are when the probability never changes, no matter how many trials you have. So if you flip a coin, you can flip a coin once, or you can flip a coin 1,000 times. The probability of getting heads is still going to be 1/2, because there's one side that has heads and there's two sides overall. Right? It's always the same. Right? Now you might get into instances where you have like 10 flips of the coin and they're all heads, and you're like, well, I'm kind of due to get a tails at some point. Being due to get something, that's not the definition of probability. Right? So we just focus on the approach. So I'll just show you. Maybe, honestly, it wouldn't really hurt to do maybe you know what, I'll do all four of these, right? Because they kind of lead into each other, so it's kind of plucking stuff out of thin air. It's probably not the best idea. All right, but if you're looking at two cards drawn from a standard 52 card deck, so just thinking about the image on the previous page, the first card is not replaced before the second card is drawn. All right, that's the key ingredient there, because if I say probability of getting a king and then an ace, king, then an ace, I'm saying the probability of getting a king, then the probability of getting an ace, given that my first card was a king. All right, so this means given that. All right, you could also say like knowing that. All right, so if I know that the first card that was selected was a king, now what's my probability of getting an ace? That's how that really reads. All right, the first part, especially with cards, should be very easy. We're looking at 4 out of 52. But then this piece, I'm saying, all right, you got a king. Not all 4 of the kings, but you got a king for my first trial. Now what's the probability of getting an ace? Though there's still 4 cards in the deck that are aces, but now there's only 51 cards overall. All right, because you got to kind of imagine, and I do it, I'm very spatial and visual. So like, I'll just imagine in my mind what's going on. So, you know, it's easier said than done in some cases, but like sometimes a quick gesture where it's like, all right, I'm going to pull a card from a deck. I'm going to look at it. Oh, it turned out it was a king. We always assume success with probability. All right. So that first card is a king. All right. Now I'm going to take that and throw it away. Now I have how many cards left in the deck? Well, I started 52. I threw away one of them. Now I have 51. Now, how many of those are aces? Well, I haven't touched the aces yet. So that must mean that all the aces are still there. That's where the 4 is coming from. Now, if we want to do this on NumWorks, computationally, I mean, the top values shouldn't be bad. When you're multiplying fractions, just be careful. You know, I know it's not like a daily occurrence that you multiply fractions, but it's always top times top, bottom times bottom. Right. So there's a couple of ways you can handle this. So we don't cross multiply unless there's an equal sign between the two fractions. All right, we multiply across. So 4 times 4 is 16. 52 times 51 is 2652. Because I'm a genius. No, because I've done the same problem like for the last 20 years. 50, like how many people could rattle off 52 times 51 off the top of their head without even hesitating? It's I've done the problem over and over again. And you'll see this number fairly frequently. And when you do, you'll be like, oh, it's always 2652. So we're good there. But if you want to put it in NumWorks, use the division key and it'll create a fraction. 4 divided by 52 gives you the fraction 4 over 52. Then hit the right arrow to get out of the fraction times 4 divided by 51. I forgot to hit the 4. 4 divided by 51. Now you have two fractions. They look good. Hit enter. It'll give you the simplified form and also the decimal form. All right. So simplified form is fine. Unsimplified form is fine, as long as they're equivalent. The decimal form is a little trickier because you got to go up to 3 significant digits. So in this case, it would be 0.00603. That's why I was saying last class that maybe you're better off just leaving it in fraction form. This way you don't have to worry about the rounding. Now, just a quick note, whenever you do a computation in NumWorks, if you go back onto the answer, I was down here on the entry field. If I hit the up arrow, you see those 3 dots up here? That means that there's more information. So I hit OK on that, and it gives me other things that I might find useful. But you might look at it and say, well, I don't find any of this useful. And in this case, that is how it plays out, but you never know what's in there. So maybe there's something that you could use. All right. But in this case, it really didn't matter for much. Now, number 2, probability getting a king and an ace. All right. Now, and is kind of a tricky concept because we don't necessarily know that the order matters. All right. So if they don't tell you whether or not the order matters, I'm taking 2 cards from the deck and I need a king and an ace. If they think about it, you're playing Hold'em, if you're familiar with that game. All right. You're playing Hold'em and you got 2 cards dealt to you. One of them is the king of hearts and the other is the ace of spades. Does it matter to you what order they came in? Those 2 cards, like you get 2 cards in your hand, you put one on the left versus one on the right. Like, what does it matter? Now, if you're getting dealt the remainder of the game, you're getting dealt cards one at a time. The order in which those cards are dealt might matter because it might influence your wagering. Like if I got a king and an ace, and then the next card that came up was a 2, then a 3, then a 7, you might look at it and say, well, I'm out because my king and my ace aren't really worth much, right? Because I have nothing to go with them. Right? I can't make a pair or a full house or anything like that. So the order in which those other cards come out might matter because maybe the very last card that comes out is another ace, in which case you have a pair of aces. But that's a risk that you'd have to take. Now, if when those other cards come out, if you got the ace first, then you might put in a big bet. I got a pair of aces. All right. So it can be tricky, but the long story short on this is if it doesn't suggest the order, then you might have to assume that either order is relevant. All right. So the way we would interpret this is the probability of getting a king and an ace, or getting an ace and then a king. All right. So actually, sorry, I meant to write then. All right. If you have 2 cards being dealt to you, it could have happened in either way. All right. You might have got the king first, then the ace, or you might have got the ace first, then the king. All right. So probability of getting a king, then an ace would be the probability of getting a king times the probability of getting an ace, given that the first card was a king. Now we've already done that. That's the same as question 1. All right. Going the other way seems different, but it's going to amount to the same thing because I'm looking at the probability of getting an ace times the probability of getting a king, given that the first card was an ace. That or implies addition. All right. Whenever you see the word or, you're going to be using addition. And that's because it's this scenario or this scenario. When you put them together to make one broader experiment or outcome of an experiment, then from there, you would have a sum, right? Whenever you're combining, combining is another word of saying addition, another way of saying addition. So probability of getting a king, 4 out of 52. You got the king. First card pulled from the deck, you got the king. Probability of getting an ace, 4 out of 51. All right. Start over, or is kind of like a reset button. Put all the cards back in the deck, because the other thing that could have happened was maybe the first card was an ace. I got the ace, threw it away. There's still the 4 kings, but now only 51 cards. So it's the same set of computations, just we're going to have to add them together. All right, so 16 over 2652 plus another 16 over 2652 is going to give you 32 over 2652. All right. So what you could do in NumWorks is take your answer. If you go up, highlight the number itself and hit OK, it'll bring it down into a new field. You take that and double it, because there's 2 of them, and you get 8 out of 663, or we could say about 0.0121. Oh, this is actually an equals. All right. That's why playing cards is so complicated, because, even with a full deck at your disposal, the probability of you getting 2 specific cards is pretty small. But when you play against other people, depending on how many other people are involved, your chances could improve. Because if like, let's say you're playing, it could even be blackjack, like you get a bunch of people at a table, and now most when you play blackjack, it's mostly double or 2 decks, but every now and then you'll find single deck blackjack. And if you do, if you're of that mindset where you like to play a game of chance here and there, if you see single deck blackjack at a casino, have a seat. It's easier to keep track of what cards are out, right? Because if there's 4 people at a table, and sometimes that's I would say my experience with single deck blackjack, it's pretty rare to have as many as 4 people, because having less cards does have a drawback, where you look at it and say, well, I need an ace, and there's 3 other people. If they get aces, then I know how many aces are left in the deck. Like each one of them got an ace. All right. So now I needed an ace, and there's only 1 left in the deck. What are my chances of getting that? But if you're playing 1 against a dealer, then it's a little bit more predictable. And also, fun fact, people really don't like you looking at their cards during a game of chance at a casino. Yeah, it's pretty dangerous to do that. So yeah, it's kind of when there are other people at the table, it's kind of harder to keep track, right? Unless you're willing to take some chances. All right. But yeah, having a familiarity with a deck of cards, like, I mean, it's a skill, it's a valuable skill. If, games of chance are your kind of thing, right? Now, probability of getting two cards of the same suit. So remember the suits: hearts, diamonds, clubs. Yeah, that never looks good. And the spade. All right. So those are our four possible suits. When I say two cards of the same suit, I'm saying, well, it could be a heart and another heart. All right. Since they're identical, we wouldn't really care about the order. Two hearts come out. Doesn't matter which one came first. Like if you're working on a flush, you're playing poker, maybe 5-card poker. You're working on a flush, and you have 3 hearts in your hand, and you throw down the remaining 2 cards. If you get 2 additional hearts, you don't care which one came first, the 2 of hearts or the jack of hearts. I got 2 hearts, now I have the flush. All right. But they said the same suit, so it could be the case that we have a diamond and a diamond. Or it could be the case that we have a terrible looking tree and another terrible looking tree. Clubs. Or the spade. All right. So just got to figure out those probabilities. Easier said than done sometimes, but in this case, not too bad. So looking at the deck of cards, again, there's 4 suits in the deck, 52 cards overall, which means that there have to be 13 hearts, 13 diamonds, 13 clubs, and 13 spades. And that gets you all the way to 52. So one way to handle this would be to figure out each of these probabilities and then add them all up by the addition, right? Addition rule. Or, as it turns out, each one of these probabilities are going to be the same. So figure it out in one instance. So hearts and hearts, and then take that answer and multiply it by 4, because again, these are all going to be the same. All right. So 13 out of 52 is the probability my first card is a heart. We always assume success. So I got a heart. How many hearts are left? 1 less than what I started with. All right. I just took a heart out of the deck. There were 13. Now there's only 12. But there's also only 51 cards in the deck. Now, if you do the same thing with diamonds, you're going to get the same outcome. There's 13 diamonds in the deck. Because remember, or is a reset button. All the cards back in the deck, new scenario. All right. There's 13 diamonds. If you select one at random and throw it away, there's only 12 diamonds left out of 51 cards. If you do it for the clubs, 13 of the cards are clubs. Throw one of them away. 12 out of 51. Same thing with the spades. So every scenario has the same probability. So you can take these results and add them all up. That would work out perfectly fine. Or you could take that 13 out of 52. So again, in NumWorks, 13 divided by 52, right arrow times 12 divided by 51. And because there's 4 identical quantities, multiply by 4. All right, so that would be the same as saying 4 times 13 over 52 times 12 over 51. And again, NumWorks gives you the simplified form. That's great. We don't need it to be simplified, but if it's going to give it to us, why not? So 0.235. All right. So
You wouldn't want to round to the nearest third, like you said on the last one.
yeah, 3 significant digits.
Okay, so for that, for the three significant digits, would you round the third digit, right? That's how you wanted it done?
In this case, yes. If there were any zeros after the decimal point, we'd have to ignore those before counting the 3 places.
Okay, and if we left it as a fraction, we didn't have to do that, right?
Exactly.
Okay, thank you.
No problem. Yeah, that's the benefit of leaving it as a fraction. You don't have to worry about the rounding. Right. And number 4, 2 cards with the same value. Well, there's different schools of thought. When you're dealing with a deck of cards, we need to have some general consensus on what rules we're following, because the value of cards change depending on the game that you're playing. Right. So what we assume is that all numbers are equal in value. So every card with a 2 on it is equal to every other card with a 2 on it. But the jacks, queens, kings, and aces are all equal to each other. So every J is worth the same as every other J. We're just not assigning a number to it. All right. So I would say the jack of hearts is equal to the jack of diamonds, jack of clubs, jack of spades, but I'm not assigning a number to it. I'm not going to say it's worth, 10 like in blackjack. So with that in mind, I would be saying probability of getting a 2 and a 2 plus the probability of getting a 3 and a 3 plus the probability of getting a 4 and a 4 plus the probability of getting a 5 and 5, 6 and 6, 7 and 7, 8 and 8, 9 and 9, 10 and 10, jack and jack, queen and queen, king and king, ace and ace. So all the way up to ace and ace. So just like we did in the last one, we'll look at one scenario. Probability of getting a 2 and a 2. 4 out of 52. Because initially there's 4 cards that are worth 2 points, whatever you want to say, it has a value of 2. Select one at random. Now there's only 3 left over out of 51. And that gives me 12 over 26, 52. All right. Now I could do what I did before, but it's actually, it would be a lot more writing. What I would prefer to do, so since I know all the probabilities are going to be the same, and if you don't believe me, then try for 3 and 3. You'll see that it's the same result. 4 out of 52, because there's 4 3s in a deck. Take one out, 3 out of 51. Multiply 12 out of 26, 52. Same for 4 and 4, 5 and 5, 6 and 6 and so. So there are a total of 13 pairs. All right. 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, and ace. All right. So 13 of those pairs. So I would take my 12 out of 26, 52 and multiply it by 13. Do that in a calculator. But it's going to be 156 over 26, 52 if you do it by hand. But, it'll give us the simplified form. 26, 52. So it gives us a result of 1/17, also 0.588. And again, go with the fraction form. Save yourself from having to worry about the rounded decimal. All right. So yeah, it could be a little tricky. I mean, if you look at like the sticker shock of this page, it's like there's a lot of stuff that's written there, like a lot of symbols and things like that. But going through it carefully, I found that with probability, my biggest issue when I was first learning it was that I very frequently neglected well, not really neglect. It's kind of tricky. I didn't take into account all possible outcomes that could exist for an experiment. Right. So I would be the one that would look at it and say, oh, a king and an ace. Well, it must be the king first, then the ace. Well, depends on the game. There was something lost in the context, so we got to be careful. On a test, the rules of whatever game would be clearly defined. I tend to stay away from real games. I just make up a game. Like you have 5 cards, each with a geometric figure. What's the probability of getting 2 squares when you select at random? Something like that. I do that for a couple reasons, but the most straightforward reason would be that it gives a finite answer that can't be, that's really not open to interpretation. It's like, well, this is the game, so it has to go this way. Because when I would give problems with decks of cards, there's some blackjack players out there that just can't get it out of their head that a jack isn't necessarily worth 10 and an ace is not necessarily worth 1 or 11. So I go with with more unique games. All right, so let me stop the recording here, or at least pause it.